In the previous video, we have understood the difference between conductor, semiconductor, and insulator. We also know that to change the conductivity of an intrinsic semiconductor materials, we need to change the energy of the electrons in the valence band so that it can have enough energy to jump to the conduction band or becoming free electrons. But the question is how to change the energy without burning it. This is where the term extrinsic semiconductor materials comes. Extrinsic materials mean we alter the intrinsic materials like silicon by adding a specific impurity atoms to that semiconductor material. This process is called doping. We can dope boron atom to the silicon. Boron only have 3 valence electrons, while silicon have 4 valence electrons. This cause an empty space when we dope boron to the silicon, and this empty space is what we call holes or lubang in Malay. Electrons is negatively charged, and because the number of electrons is less in this material will be more positive than pure silicon. That is why we call this material a p-type material. Although there are no free electrons in this p-type materials, as you can see, electron can still move around because of the existence of the hole in the valence band like this. That is why it still can conduct electricity without the need for us to burn it. But it is much slower than the free electrons because we need to move through the hole locations that is existed inside the material or inside the bonding. So how to make it faster? We need free electrons. How to add free electrons to the material without burning the material? To create free electrons, we add donor dopants or donor atom to the silicon. The silicon is doped with phosphorus that has 5 valence electrons. Since silicon can only bond with 4 electrons, 1 more electron will become free from any bonding and can move around freely. Now we got free electrons in our materials without the need for us to burn it. Since electrons are negatively charged, and because the number of electrons is higher in these materials, this material will be more negative than the pure silicon, and that is why we call this material an n-type material. And when we combine these two types of materials together, the p-type materials with many holes in one side and n-type materials with many free electrons, it will form a diode, and this is how a diode is born. When these two materials connected, it will have a charge difference at the joint, which we call a p-n junction here. And like a magnet, different charge attracts to each other. Since electrons are negatively charged as opposed to the holes which is more positive at this junction, these free electrons nearby will be attracted to the nearby hole, making these free electrons jump into the hole or recombine with the holes. And this process will keep on going until the distance between them is far enough to be attracted to each other. Just like a magnet, if the magnet is too far from the other metals or magnetic materials, it will no longer be able to attract to each other. This will leave this space here without any free charge that can move and separate these two materials here, and this separation here is called the depletion region. Alright, can you follow so far? If you are lost, feel free to rewind this video and watch it again until you understand. And now, what will happen when we supply a voltage to this device? There are two conditions that we can analyze. The first one is when we give positive voltage to the p-type materials and negative voltage at the n-type terminal. Electrons will come out from the negative terminal and comes into the n-type materials. Again, remember, electron is negatively charged, and similar like magnet, same charge repel each other. So this electron will push the free electrons in the n-type materials and it will come into the depletion region. Now, this side of depletion region is more negative than this side. Since this is more negative, what will happen? It will push the negative charge from these sides here, so that the size of the depletion region here will become similar again, and now the depletion region become smaller. But as you can see, no electrons left this device yet, meaning that no current flows yet. What will happen now? We increase the voltage further, and by increasing the voltage further, more electrons coming in through the n-type materials, which then will push the electrons inside the n-type materials into the depletion region, which then pushing more electrons out of the depletion region. And if we add more electrons again, we increase more voltage, increase the voltage further. So what we can see, it will push these electrons here into the depletion region, and now the depletion region will disappear altogether. And as you can see, the electrons is start coming out from this sides here, which can then flow in back to the positive terminal of this power supply. And if we increase more electrons will flow in, push away. The electrons keep on moving and coming in into the p-type materials and continue flowing. Now there are flow of electrons, meaning that there are current flowing at the opposite direction of the electron flows. So if we increase the voltage further, electrons can come into the n-type materials, current will flow. And if we increase further, more electrons will flow. The higher the current, the I will be like shown in this graph here. But don't increase the voltage too much, because the current will increase drastically, and if the current is too high, it will break the device. This device is now conducting electricity, and all electrons move forward, so we can call this condition as forward bias. The minimum voltage to make this device start conducting is called forward bias voltage, VF, which is usually rated at 0.7 volts for silicon and as small as 0.3 volt for germanium. Now remember this value, write it up, paste it up anywhere that you can see, because we going to use this value until the end of this course. So please remember, silicon is 0.7 volts and germanium is 0.3 volt. So how was it now? Interesting, isn't it? Again, if you are unclear in any part of this video, feel free to go back and watch it again as many times as you like until you understand it, or just ask me. Easy peasy, I will be more than happy to help you. And as I said before, there are two conditions that we can analyze. The first one is when we give positive voltage at the p-type materials of p-type terminal and negative voltage at the n-type terminal. The second one that we will cover is when we change the polarity of the supply voltage with the negative voltage at the p-type terminal and positive voltage at the n-type terminal. When we do this, electrons will come in from the positive terminal, comes in from the p-type terminal. And when it comes into the p-type materials, it will push the electrons inside the p-type materials and it will recombine with the hole until the end of the parts where it cannot move anymore, because there is no free electrons or holes that it can move in between, and therefore it will stop here. And because this part here is becoming bigger, so what will happen, this becoming more negative, so these electrons here will be pushed away, and as you can see, the depletion region become larger. And if we increase more electrons or more voltage that we supply in, electrons will come in to the p-type materials again, and it will move in between the holes just like before until there is no more free carrier. So again, depletion region become larger, which automatically will push away this electron, since this part here is more negative, to make it more stable again. And now the depletion region becomes larger, and as you can see here, only some electron is moved out from this device, and this electron is actually originally from the n-type material. It is not the one that is coming from the p-type materials, because the one that coming from the p-type materials and only recombine at the holes. So all electrons just recombine with the holes, forming a bigger depletion region, as you can see. So, and only electrons from the n-type materials is leaving this device, which makes it very few currents, just a few values of currents around pico or nano ampere only, too small, just like nothing, just like there is no current exists. And at this condition here, we call it simply like a switch is being turned off, so it is not operated. In other words, how large the voltage we supply on the depletion region is getting bigger and bigger. No increment of current flow, and current stays at a very low voltage, almost non-existence, just like it doesn't exist or it doesn't conduct electricity. If you try to increase the voltage more, it will just break. So be careful, because the depletion region will become too large. The electrons, free electrons, will start to disappear from the device, so it just cannot operate anymore. So be careful, don't operate a diode at more than the breakdown voltage value. Since now the connection is in reverse direction, the movement of the carrier also in the reverse direction, we call this condition here a reverse bias. So that is the two different conditions of diode operation, the reverse bias and forward bias, where forward bias is making the device on, whereas the reverse bias is turning the device off. Forward bias is giving positive voltage to the p-type materials, whereas the reverse bias is reverse the polarity with negative voltage is applied to the p-type material. And finally, forward bias is making the gap between the materials or the depletion region smaller, whereas the reverse bias is making the depletion region larger. Since it can only operate in one direction only, that's why the symbol for this diode is the arrow showing the direction of current, which is from positive terminal or p-type materials, and block any current comes in from the negative terminal or the n-type material. The positive terminal is called anode and the negative terminal is called cathode. There are a lot of types of diode, but the basic symbol is still like this, with some additional symbol. For example, the Zener diode with a Z at the cathode terminal, a light emitting diode or LED with the arrow move out symbolize the light is emitted. Photodiode with the arrow move in symbolize the light is received or detected. Schottky diode with S at the cathode terminal, tunnel diode with a tunnel shape at the cathode terminal, and constant current diode with I represent current symbol, and many more diodes other than this. All all diode or all symbols, all principles based on the same basic symbol and basic principle that has been explained here. In this course, we will only cover the basic diode operation in chapter 2 and the Zener diode in chapter 3. So stay tuned to the next video. Hope you understand the explanation in this video. If you are unclear in any part of this video, feel free to go back and watch it again and again and again and as many times as you like until you understand it. Or just ask me, don't be afraid, I will be more than happy to help you. And as usual, if you like this video, hit the like button and consider yourself subscribing to this channel. And stay safe, stay curious, and stay joyful. I'm Ikhwan. May God bless you. Assalamualaikum.